Okay, so now we are on to chapter 4, and chapter 4 is going to be talking about control volume analysis. Okay, now why do we say control volume instead of open systems? Okay, we're controlling the volume. We're controlling that this volume is what we're going to look at. We're not controlling the mass inside that volume anymore. We're just controlling that volume. Now, really, a closed system is a special type of control volume in which the mass doesn't change. That's really what's happening here. So I could go and talk into about closed systems and say, hey, what's your control volume for a closed system? And you would say it's it's the air inside the piston cylinder, and that would be okay. But we do make that delineation here in this next chapter. We talk about control volumes. We're now looking at a control surface, and now mass is going to cross that surface. Okay, so the control volume we say is mass may cross the boundary. Okay, that's what's going on here. Now, so I have a little proof here. I have to go with the proof a little bit, and so what we're going to do is we're going to draw this weird cross section of a container. Let's make it a big tank, and it's got a pipe coming into it. It's got a pipe going out of it. Okay, so I want to make my control volume, I want to make it equal to this big portion here of this tank. Put a dotted line here. And there is going to be some mass of my control volume at time t here. I'm looking at there's mass of control volume at time t. And I want to, I'm going to put in some mass. Okay, this is going to be my mass coming in. Okay, this mass is going to come into this control volume. So I want to look at both these things, both the purple and the green here. I'm going to watch that. So, so at time t, what I have is my total mass that I'm looking at is going to be equal to the mass of the control volume at time t plus the mass coming in. That's what I'm looking at. And I want to time this until all of that mass comes into the control volume. So what I'm going to do here is draw this exact same shape. Beautiful copy. I mean, it's just artistically stunning how identical those shapes look. And so we're going to look here. And now we have the mass of the control volume at time t plus delta t, because there has been some time where that mass has come into that control volume, and it's going to be mixing up here, and it's going to push out an equal amount of mass out the other side. Now it happens to be it's a little bit smaller diameter, so it's going to look a little bit longer, but this is my mass exiting. Okay, so I can say at time t plus delta t, my total mass, now it looks a little different, but it's the same amount, is mass of the control volume at time t plus delta t, plus my mass exiting. That's what's happening. Now we know mass cannot be created nor destroyed, so the mass total in both of these cases has to be the same. So I'm going to say the mass of the control volume at time t plus my mass coming in must equal the mass of my control volume at time t plus delta t plus my mass coming out. I think you will agree with me that is true, because mass cannot be created nor destroyed. Let me put that here. Mass cannot be created nor destroyed. Anytime we can get to use the word nor, that's a good day. It's a good day. Okay, so now I want to take this equation, I want to manipulate it a little bit. I want to rearrange it here because I don't like it in its current form. So I'm going to say the mass of control volume at time t plus delta t minus mass of the control volume at time t is going to be equal to, well, that's going to give me mass in minus mass exiting. Okay, that makes sense. That makes sense, completely makes sense. If I take the mass in and minus the mass exiting here, if it's the same number, I'm going to get 0, and I'm going to have the same mass in my control volume at time t plus delta t as I have at time t. Okay, that makes sense to me. I mean, let's be honest. We've all taken a bath at one point in time in our life. In fact, your assignment this weekend is to take a bath. Okay, and you're going to look and you're going to sit in your bathtub, and you're going to know, hey, this is the mass. My bathtub is going to be my control volume, and you're going to say, here's my mass and my control volume at time t. And then you're going to turn on the water, and you're going to put some mass coming in, and you're going to see what the mass of the control volume at t plus delta t is. Okay, and maybe then you'll instead of turning on the water, you'll open the drain and you'll let some water go out, and you'll say, here's my mass, and here's the water going out. And you'll see how the mass of the control volume changes with time. And if you're really crazy, what you'll do is you'll turn the drain on, you'll open the drain and have the water coming in at the same time. Okay, and you'll see what happens. Am I in a steady state situation where the mass of the control volume doesn't change? Or am I in a situation where the mass of the control volume is changing, lowering, or is it rising? Okay, so yeah, tell your roommates, I'm sorry, Dr. Wanklin has required me to take a bath. I haven't taken a bath in 15 years, but I'm going to take a bath tonight. Get some bath bombs, get some Enya going on, some I don't know if you know who Enya is, some really, whatever, get a candle or two, pull out your thermo book. It's going to be good stuff. Unless your thermo book is electronic, it's probably not a good idea. Your appendices. You choose your appendices. Try not to get them wet. But that's a requirement. Okay, that's a requirement for this weekend. Just you have to do it. Okay. Now back to thermal. We've done a lot of the sides today, huh? So let me tell you that we're not worried about this over a long period of time. We're worried about this mass equation on an instantaneous basis. Okay, what did we do in this class when we wanted things instantaneous? Well, we divided everything by delta t, right? So I'm going to divide this side by delta t, and I'm going to divide this side by delta t. And what I did was I took that and I took the limit as delta t went to 0, and I saw what happened to this equation. Now, some of you are getting very excited here because you're looking at that left-hand side of the equation. You're saying, look, that reminds me of something from calculus. And this right here is the definition of a derivative. Okay, definition derivative. So we can write this as the change in mass of the control volume with respect to time is equal to, well, what do I happen when I take mass divided by time and set that equal to 0? Remember what I did with work and heat? I said this is m dot n, the rate of mass flow rate n, minus the rate of mass flow rate xing. So m dot n minus m dot xing. So let's put this in words. This is going to be the rate of change of mass within a control volume. Okay, this is the rate of mass flow in. And this is the rate of mass flow exiting. Okay, very simple. And this equation here is going to be called the conservation of mass equation. Oh, come on, pen. Equation, or I call it the continuity equation. Okay, because it's dealing with the mass continuity. So I might say conservation mass, or I'm often going to say continuity equation. Okay. And you don't just have to have one inlet and exit here. We can really should write this as dmcv over dt is equal to the summation of all the mass flow rates in minus the summation of the mass flow rates out. Sure, I mean, this is perfect. You go ahead and when you're in that bath, turn on the water coming in, open up the drain, and then get a hose from the sink and fill it up too. Get a couple things coming in. Maybe have a drain going into the, I don't know, suction, a siphon going in, taking water out and put it in the toilet. I mean, God, I can't even imagine how much fun you're going to have with this. It's just going to be awesome. Okay? So this is our continuity equation. This is what we're going to be talking about today. Pretty straightforward. We're going to go into a little bit more in depth in it in just a second.